Folks, this is video number 35 that I'll be doing. And in the previous videos on composites and the use of the CATIA's native FEA solver to analyze them, I concentrated mainly on unidirectional plies. There were a few videos done on honeycomb and a sandwich plate with a foam core, but I never actually did a problem with fabrics. Okay, so in this video, I'll show you how to model the problem if you're actually told that the plies are not unidirectional but woven fabric, and do a simple problem. Okay. It does require the first 4 or 5 minutes though require some explanation about the fabric and the difference between it and a unidirectional ply structure. Okay, so let me go here. All right. First of all, we all have an idea of what a fabric is. The clothes that we wear, the rug that we sit on, etc. Those are woven fabrics. Okay. And in a woven fabric, the simplest one that is shown here, you can see that there are two directions, two primary directions. One of them is called the warp direction. The other one is called the weft direction. The perpendicular to that is, of course, a normal that we're not interested, at least in this explanation. Now, in the plane weave fabric, the direction warp and weft have no preference. You can see that, for example, if we just hypothetically we had a different strands in the just hypothetically in the weft direction, different material, different number of different width of these green bundles as opposed to the yellow one, then of course there are preferential direction. But a plane weave means that the things are identical in the two directions. Okay. Now, by the way, these may be stacked on top of each other. In fact, very frequently to use plane to use fabric, you just use a manual layup or some automated structure to stack them on top of each other in different directions. Okay. Now, uh, I'm going to be only concentrating on this. However, I want to after we discuss this thing, you'll notice that even if that is not the case, the process of modeling it in CATIA is the same. Now, if you look at each one of these yellow pieces or the green pieces, is actually a bundle of many carbon fibers, for example, or some other fiber together. Okay, and these are called yarn. Okay, so this is a yarn. It's these yellow thingies and the green thingies, and then they go like that. Okay. Now, in general, woven fabrics in general, although it is possible to do a manufacturing process where the worn and the warp and uh, weft directions are not orthogonal to them. But if you look at your clothes, for example, they are orthogonal to each other. Okay, but they don't have to be. Okay, now. Uh, Woven simply means that uh, the 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 yarn passes over and under uh, uh, the, uh, the the warp yarn, okay, in a fixed uh, setup. And let me put it this way: it is possible to have these yarns sitting next to each other and either somehow fixed in place using the resin, or stitches, little stitches that keeping them together. But the word fabric means that the yarn, that 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 bundle that I showed you of, for example, carbon fibers, it passes over and under the warp yarns in a very fixed uh, pattern. Okay. Now, plain means that it goes over and then under immediately, over and then under, because that does not have to be the case, because there are fabrics that you skip a few, for example, bundles, three, and then you go over and under again, skip a few, go under, over, etc. For example, a satin fabric, which is very soft. I'm sure you have experienced that, is a situation where it doesn't go over and under uh, immediately. Okay. Now, when it comes to modeling fabrics, irrespective of how they are, whether they're plain or they're Saturn or they're some other kind, you pretend that it was actually a regular ply, unidirectional ply. Okay, that's a bad way of saying it, but you can use the same things that you did for unidirectional plies, except that you have to give the material property somehow. Remember, for a unidirectional ply, what you do is you give Young's modulus or modulus in longitudinal and transverse direction. You have a Poisson ratio in the plane of the in the plane of the ply, and then G, shear modulus in the plane of the ply, and then two other moduli which are perpendicular. You need those numbers, okay, for a fabric. So somehow either you have experience and you get it from supplier, get those numbers, or you go to some micromechanics software which produces those numbers for you. Okay, of course it's approximate, but it's better than just guessing them. Okay, so my point is that either you do experiment to get those necessary data for the fabric, okay, and or you use a micromechanics software to get them, or you can estimate, very rough estimate, based on what you know, what the bundles are made of, and what your resin is, and the volume fraction, you can estimate the properties that you're looking for. Now, there are two crude ways of estimating these. When I do the example for you later today, I'm not going to be estimating. I'm going to use the data, a table which gives it to me. But what I'm saying, there's two ways of doing it. One is to pretend that this woven fabric, plain woven fabric, is actually separated into unidirectional plies stacked on top of each other. This is only a rough estimate, or you replace it with a single layer of 2D orthotopic material. Okay. Now I'm going to leave these things on the screen. These are taken from the textbook by uh, uh, Daniel Gay and Stefan Stefan Tsai, and you can consult them. But so I'm not going to worry about these things. I will just do the problem as I need it in this video segment. However, these things are important, so I will leave it for you on the screen to take a look at it, or consult the textbook. Now, the first one that I showed you immediately before this thing was taking your plain fabric and basically decompose it into two unidirectional plies. This one is estimating the estimating the four numbers that you want based on what you know about the unidirectional one. And this is a textbook that I was talking about, and I'm going to be using a plain plain weave fabric, carbon fabric, carbon epoxy. Uh, Combination, and these are the four numbers that I'm going to be needing. So because it's a plane weave, EX and EY are the same, there's no preferential direction, EX and EY are the same, and shear modulus is given here, and the Poisson ratio. Now Poisson ratio for a fabric is a lot smaller than the one for unidirectional ply, and so typically for carbon epoxy, uh, unidirectional, it's about 0.25, 0.3, something like that. Notice that this is 5, 6 times smaller than those. Okay. Now, it's this table refers to balanced fabric. All that means is that the bundles in the X direction or Y direction, namely in the warp direction and the weft direction, are identical. Okay, as far as the number of fibers in a bundle, etc. Okay, this is the problem that we're going to be doing. It's good because when it comes to modeling it, first of all, we use a fabric, but it really doesn't matter. It could have been a unidirectional ply. All you need is those numbers. but it also involves one that is dealing with contact. So I have a rather long plate, and the ends are clamped, and there is a mandrel in the middle, exactly in the middle. The dimensions are given here, which is resting against the top of the uh, plate, and then pushed down by 5 millimeters. Okay, so here's the situation. This is the surface. This is the surface that we're going to model, and then the mandrel is going to be done as 3D object, okay, 3D solid. Uh, and the properties of it really doesn't matter because we are assuming that this does not go through much deformation. In fact, many other software allow you to define rigid bodies or analytical surfaces instead of modeling this thing and meshing it with 3D elements, but we don't have that luxury in CATIA. And yeah, so uh, when it comes to actually modeling this thing, the material modeling, we're going to pretend this is as if it was a unidirectional ply, but the direction is given. For example, the first layer. This is the top layer. The top above the plate is 90 degrees and 0 degrees. Okay, so basically, if you had a rosette, and if you treat this thing as if you were doing unidirectional ply, it'll be 0 degrees for the top one, and the bottom one is the fabric rotated 45 degrees, so it's going to be uh, angle between X and this fiber, for example, is 45. Okay. Yeah. So, the way I'm going to model this thing, as I said, this is the typical numbers that I'm going to be using for the mesh size and for the solid and the shell. And because it's an assembly, I'm solving it as an assembly problem. You have to create analysis connection between them, and we're going to declare that analysis connection as contact. Okay. All right. So let me put this thing in front of me because I need that. And we're going to go. Incidentally, this problem has two planes. One plane, actually, this plane has two planes of symmetry. In other words, instead of modeling this, I can cut this thing in the middle in this direction and along the length direction and model a quarter of it. But in many cases, the composite may not be symmetric, so we got to be careful. I'm going to model the whole thing. Definitely, there is a one plane of symmetry here. The other one, I have to think about it. But anyway, we're going to be modeling the whole thing. All right. So first thing that we need to do is to create our material. So we go start, infrastructure material. I'm going to call this thing fabric. Plain weave fabric. How about that? Plain weave fabric. And then on the composite, now notice that when you go to composite, it's talking about unidirectional. We know what it is. It's bidirectional. Bidirectional is the case that we're dealing with. However, these radio buttons, they don't matter uh, in CATIA. It's okay if you're creating a bill of material, but for analysis purposes, it doesn't matter whether I declare it unidirectional or bidirectional or leave it as any one of these other things, because I still have to input these numbers, and it really doesn't matter. However, to be strictly uh, correct, it's not correct. Okay, I'm gonna I'm gonna choose bidirectional, and the thickness, cued thickness. If you look at this thing, the cued thickness is 2 millimeters. This total is 4 millimeters. A fabric is laid on the top, a fabric is laid on the bottom. So the thickness of each of these fabric plies or sheets is 2 millimeter, 2 millimeter, 2 millimeters. Okay. So this one I'm going to make 2 millimeters. All right. And really, as I said, these things don't matter. You go to analysis, you do 2D orthotropic, and just put in those numbers that you have in your table. So for Young's modulus or Poisson, Young's modulus, elastic moduli, we put 54, 54, 54,000, 54,000. 54,000. Poisson ratio, I believe it was 0.045. Is that correct? Check that. 0.045, and shear modulus 4,000. Shear modulus in this plane is 4,000. And in the other two planes, I will use same as above. Okay. If you have the actual data, use it. But if you don't, use I always use the same value or something of the same order of magnitude. Okay, that takes care of everything that we wanted to do here. We say okay. We're gonna save this thing. I already created a folder there called Plane Weave Desktop, Plane Weave or Woven Fabric. So I'll call it Fabric. I'll call it Plane Weave. Carbon epoxy. Okay. So we created our material. I'm done with this thing. Now we're going to create the part. Okay, so we need to create an assembly because this is going to be done as an assembly made of two parts. One of them is that plate, and the other one is that mandrel, and we'll take care of it. So we start with the product file. Immediately, I'm going to save it in the same folder. So we go File, Save Management, Save As, and this is the right folder. And I'm going to make my first part. So Insert, New Part, in there, and I'm going to call this thing Right-Click Properties Plate, and this is the plate. One is the part name, which is Catia calls it part number. The other one is the instance name. And these are the instance name is important when you have an assembly. Okay, let's go make the plate. Double click. I double clicked on the plate. I'm going to go to generative shape design. Basically, make a big rectangle. So on a convenient plane, on that horizontal plane, I will sketch. Okay, a rectangle. Why don't I make it centered? This really doesn't matter, but I'll make it centered. Okay, so the length of that is 1,000 millimeters, and the width of it is 500. No, 250. Sorry, 250. Okay, exit. Put a surface through it. FIL, FILL, fill, and I always join it. Because when I do, I can control the direction of the join, which is always opposite to the direction of the shell elements. All right, good. We also need a rosette, so let's create a rosette here. A coordinate system, axis system. That's what I'm referring to. Let me. It's ordinarily it puts it right at the global origin, but I want to see it. So let me move this thing to the left so that it uh, doesn't block the view. So let me go, yeah, oops, maybe minus 100, maybe minus 200, 200 millimeters. Okay, so, oh, I put it over there. Okay, fine, that's fine. And uncheck the current, and we'll move on. So this is going to be the rosette that I'm going to be using for positioning these fabrics on the plate. Okay. Now, we have two options. We can create our price right here, right now, and let's do that. So we're going to go to generative shape design. Well, I'm sorry, what I meant was that we go to composite design, uh, define the parameters, composite parameters, add a material. Remember I created that folder, so we go there, desktop, it was called plain V fabric. This is the material that I created, and we say okay. So there we are. And for Rosette, we're going to add a Rosette, select the one that I picked, okay, and we don't need this, okay. And that's pretty much our directions. We don't have to do anything special because we already have the 0 degree and we have the 45 degree. Obviously 90 and minus 45 are going to be you know, are not, I don't need them because I'm specifying the properties of this fabric along the 45 degrees, and minus 45 degree is going to be, if I did create it, it's already in the table. It says EX and EY are the same. So the longitudinal and transverse direction for the material that are created are the same. So we don't need it. Okay, good. Now, the next thing is the usual process of creating your group, Plies group, right there, Plies group. The surface is right here. The draping, I'm going to make it, uh, I always like to go upward, really doesn't matter, and lock the plies for draping direction. We always check, make sure everything is okay later on. Okay. So there is the plies group, and now we create our plies manually. So the first ply in that group, the boundary is that sketch that I created. Remember, I created the sketch to draw the to draw the rectangle. Well, attribute is material is correctly picked and the direction is 0. And what that means is that this first ply that I'm creating, actually this is the one, because of the way I did the draping direction being up. Remember I changed the draping direction so it's up. So this is going to be the bottom one. The first ply is going to start from the bottom, okay? So it's going to be 45, okay? And that's pretty much it. We're going to check that, okay? The second one in the same plies group, the boundary is the same, that sketch, and the attribute is going to be 0. We can check that, okay? Yeah, all right. Now, how do we check it? If you go to Ply Exploder, right there, see that? Plies group, show it to me, right there. And if you ever forget about these colors, let's go and get the, the, the compass that I hit. It's right there. You can see that? So the bottom one is the red one and it's 45 degrees. You can see that. And the top one is the 0 degrees, right there. All right. And that's it. Cancel that. Very good. So save everything. And the way I save everything, as I've said before, I always go to the product and I click on the floppy. So it saves the part for me. Now, I'm going to insert the mandrel. So insert a new part. I will say no. Let's create a mandrel. First of all, rename this thing. Properties, mandrel, or the punch, I'll call it the punch. Punch. Say okay. Let's go make it. On a convenient plane, on that vertical plane, I will sketch. Go to part design, obviously. Sketch. I'm going to draw the mandrel like this, okay? And I make sure that it is actually these dimensions are set, and this distance is 2 inches, 2 millimeter. However, I want to point out that you don't have to be that precise. You can create this mandrel anywhere you want, and then later on bring it and assemble it. Now, I'm not going to worry about this business of assembling a part and constraints and things like that, but I'm just telling you, if you already know assembly design, you know that you can draw the part anywhere and then put it here and position it according to the assembly constraints that you have. But I'm too lazy, so I'll do it right here. So I will sketch that profile that I showed you, and I'll fix it in a minute, something like that. Okay. So let me dimension these things. This, I'm not sure if these two are tangent to each other, so probably they're not. This control that, I'm going to make a tangent if it's not already tangent right there. All right. Now this height is 50 millimeters, and this radius or diameter radius is 15. The radius is 15. So there's the mandrel. Now I'm going to position it so that this is axis of symmetry. So the way to do it, you select this point, control that point. There are different ways of doing it. You can use dimensional constraints and things like that. So left point, right point, middle axis, and then you say symmetry right there. Instead of me putting dimensions here, make sure that this dimension is that much, etc. So, and then the distance from the top to that surface, distance from the top to that surface is 65 plus 2, 67 millimeter. So dimension between that top and this guy is 67. So I'm making my part in position the way I want it. And I said that generally speaking, this is not the way you do it in assembly design. You create it any way you want, and then you just use the assembly constraint to put it in the right position. Now, we're going to pad this thing by this length. So I'm going to say pad, mirror extent, in each direction 125, which means the total distance of 250 millimeter. There we are. Okay. Now, while we're at it, let's add material to this thing. So let's add material to this. So where is this? Right there. Apply material. We make it out of steel. Steel on that part. On that part. And we say OK. All right. So that's all we need, actually. Let's save everything. Go back all the way to the top. All the way to the top. And then save it. See, the disadvantage of doing it the way I did, if I ever move these things apart for some reason, then it's going to stay in that position because there are no constraints. If I had put constraints there and updated the constraints, it would have returned to where it's supposed to go. Okay, good. We are done. So let's go ahead and apply our create. There's two ways to proceed right now. One is to go to the generative structure analysis. Catia sees a solid object which has a material on it, immediately meshes it, and it uses the right property. Okay. On the other hand, if I go to the advanced meshing tool, uh, uh, I suppose we can do that too. Let's do that. Let's go to the advanced meshing tool. Okay. You can do it both ways. It really doesn't matter. So I went to the advanced meshing tool. When you go to advanced meshing tool, this thing is not going to get meshed. Okay, you can mesh it, but I'm not going to do that here. But the surface I'm going to do. So here's a surface mesh here. On that surface, 10 millimeters. parabolic, quad only. Remember I had these things here, okay? And then we say okay, and then you mesh it. This is what you have been doing for the last so many videos, 30, 34 videos. And then this is it, exit. Okay, it's meshed. We're going to look at it later. So now we're going to go to generative structure analysis. Katia sees a solid object, but unfortunately it doesn't mesh it right away. Okay, if I had gone to this workbench first, it would have meshed this thing, would have picked up the 3D property, and I had one less step to do. So as a matter of fact, let me do the following. Let me close. See, now I have to mesh it. When I measure it, it's solid element, it doesn't have 3D property, okay? So I have to go and create the 3D property. But if I had gone to the generative structure analysis first, it would have meshed this thing and I had one less step to do. So here's what I'm going to do. Unfortunately, okay, I didn't do that, so we'll stop. Okay, so here's the situation. I mesh it right there. This is a Oxy Tetrahedron Mesh. So you select that, and I'm saying that use 10 millimeter for the size. So this is 10 millimeters, okay, parabolic. And you can look at the mesh, by the way, right click mesh visualization. It shows you the both meshes. So let me change the rendering here, right there. It shows you the shell mesh, it shows you the mesh that I did. But what I'm saying is that close in on that circular cylindrical patch, do a finer mesh, okay? So what I'm going to do here, deactivate this, deactivate that. Now how do I make a finer mesh around this bend? So if you go to the place that I actually meshed it with solids, if you look at the next toolbar, this one says local mesh size. See that right there? Local mesh size. If you want to see a little bit more about this, go to the FEA playlist and look under local mesh refinement. You click on it, it says, where do you want to make it smaller? Well, I go and select this cylindrical patch here and put 5 millimeters there. And we say, okay. If you look closely, you see that a tiny little element has been created here, which is smaller than that. Okay, now look at the mesh now. So right click mesh visualization. So you can see that this is the original mesh with 10 millimeter. Then I made a local mesh refinement down here. And of course, this is my shell mesh. Okay, good. Deactivate this. Now, here's what I was talking about. Unfortunately, because of the way I did it, if I had if I had come here first, it would have meshed this thing exactly as it's supposed to be, and it would have picked the right material, okay, which is steel, by the way. But because of the way I did it, I first went to the advanced meshing tool, and I had to do this thing myself. Notice that there is no property associated with it, okay? So the different ways of doing it, one is you create a user. First of all, you create a material here, and it was steel, right? Steel, user material, uh, steel. Notice that the user material has been created and it's right there. So basically the first thing that I did up here in the material is not going to help me. Okay, now I'm going to say 3D property right there. You see that 3D property? You click on it. It says what is the support? The support is that solid mesh that I created. Okay, this, all right. And user the material. It's good that actually it picked it up, okay, because I defined steel on the top, it picked it up. If I had not defined it on the top, then I would have to create uh, yeah, then I would have to create a user defined. Okay, so you know what the thing is that this is fine. I don't need this user one because the steel was already assigned in the part element. I did not have to do this. If it was not assigned there, then you would have to you would have to create a user. Okay, so delete this. That's fine. This is going to do it. All right. Now we're going to do import the composite properties. What is that? Import composite properties. The surface is right there, and the plies. We're gonna do it by plies, and the plies were already created. They happen to be under plates, under punch. I call one of them punch, the other one plate. That's okay. Uh, what are the composite properties? Oh, no, this is the not the punch. I'm sorry, plate, right there. Punch is that steel piece. So there it is, ply group, and it's symmetrically located above and below that surface. Okay, so this is checked. Symmetrical is checked. Very good. Now I'm going to clamp these ends, and I'm sure you know by now, if I try to clamp it, it won't do it because there's a whole whack of things that are blocking my view here. One of them is a stacking branch. Let me hide this. And the other one is that sketch. See that? Sketch is still there. So let me go and hide the sketch. Now I can select this end, and I can select this end. With those things showing on the screen, I will not be able to pick those edges. Okay, now I would like to move this thing down by 5 millimeters, I believe 5 millimeters. So what I'm going to do is I'm going to say, okay, you know what? User-defined restraint on that top. Now, first of all, because this is a solid element, does not have any rotational degrees of freedom. Don't do anything. So check all of these. Okay, check all of these. So it says that uh, these are fixed. These points are fixed. Okay, well, they're not fixed. I know that. I'm going to be pushing it down. Now, to push it down, you have to go to enforce displacement. Under load, look at under load, where you see the pressure and the force and everything. There's this thing called enforce displacement. And you select that restraint that you put in there. Remember, just now you put a restraint there. Let me show you. This is the one that I just did, right now, this, okay? These things on the top. You select it, and you say, push it down by minus 5, minus 5 millimeter, okay? Keep those things as 0 and 0. We just basically are pushing it down, that's all. We say, okay? So basically that becomes our load. You can see that? Because you have to apply force up there, but we don't know what the force is, that's the thing. We apply displacement. All right, now we create, if I run this thing, it will bomb out because this will go through that part. It has no idea that there's a part sitting there. So you create an analysis connection right there. See that? General analysis connection between, I'm going to select the bottom surface of this as the first component right there. And for the second component, make sure you select this. Second component, you select the surface. Okay, surface means that this plate that you created. And we say, okay. All right. Now you create a connection. It still doesn't know what kind of a connection it is. Okay. So we're going to declare it as a contact connection. In other words, you cannot penetrate that top circular patch, cannot penetrate this. So where do we do contact? Look at the face-to-face connection properties. That's here, right there. See that? Under connection, this toolbar is called connection properties. The second one is called face-to-face connection properties, right there. And we want contact, which is right here, contact. You can select it from the screen, it's that little red thingy, or you can do it from the tree, or whichever you prefer. And it puts this icon here. It looks like something cannot contact something, cannot penetrate something else. That's the icon for contact. And don't do anything here. Just say okay. If you want to know more about those buttons that I don't do anything, you have to go to other video tutorials outside of the composite playlist. Okay, let's save everything. File, say management. There's the analysis. I haven't saved this thing. Save as. In that folder, analysis 1. Say okay. All right. and pray. Remember, this was the parabolic one. Everything was parabolic. If you had chosen linear, it would have run faster. And the results, at least in this problem, are not significantly different because the mesh was relatively fine, very fine. But done. Okay, so first thing we're going to do is we look at the deflection right there, 5.2 millimeter. Remember, you push this thing down 5 millimeters, so it pushes the plate down. And change the rendering here. See now, material shading. Except that it also shows me all this garbage here, which is the contact elements and things like that. So I double clicked on the plot on the screen, and I say on the selection, just show me the 3D solid element and the surface. Don't show me all those intermediate shell elements. Now, incidentally, if you want to see the elements, you go there, click on this question mark. All right. Now, one thing you notice is that if you look at the front view, side view, it and you zoom in, notice that there is a little gap here because it is accounting for the 2 millimeter thickness of that shell. Remember, you put a ply here, right? You put a ply with a thickness of 2 millimeter. So that distance is basically you're taking this thing, you're pushing it down, is 5.2 millimeters, okay? That distance is 2 millimeters. Good. All right, now that takes care of this. Now, if you want to see the stress, here's the one meso stress. You click on it, it only shows you the stress in the steel part. That doesn't surprise you because with shells, composite shells, there's a very special way of showing, displaying the stresses. You cannot do it with this. In all the 34 videos that I've done so far, this was never used to display the shell uh, or the composite stresses. Okay, so let's go back here. Let me deactivate this fellow. Okay. So remember what we used to do? We put the cursor here, right click, generate image, filter under stress, uh, full stress component. Okay. Now what are we plotting here? So you double click on this, double click on that, and on the visualization, if you want one mesos, it's right there. Okay. And which layer is this? Well, you go here. This was layer 1. If you want to go to layer 2, you go to layer 2 right there. And anything else that we have done before in the last 34 videos, you can use or to proceed with analyzing the stresses in the fabric, etc. So these are 2 layers of fabrics. Layer 1 is the bottom one, which is oriented at 45 degrees, and layer 2 is the top one, which is oriented at 0 degree. Okay, I don't have to say 45 and minus 45 because these are plain weave fabrics. If the orientation of one of those yarns was in 45, the other one is minus 45. Now, the last thing I want to show you today is I want to know how much force is needed to actually push this thing down. Okay, remember I said push it down by 5 millimeters. The question is how much force is needed. So what you can do is you can go here. These are all done in videos on FEA, not in the composite playlist, but I mean, if you need help, you should go there. Right click, it says on the sensor at the bottom, of the 3 sensor, right click, Down here it says create reaction sensor, resultant sensor, uh, create resultant sensor, and here we say, for example, reaction sensor. It says where. Well, remember this is the restraint that I use in order to push this thing down. If you select this, because it's waiting for you to select it, and then uh, make sure that the access system is global here, global, and update result. It tells you that you need uh, 43 kilonewton. These two are zero. These two are zero. It needs 43 newtons downward. You have to apply 43 newton downward in order to make sure that this mandrel, this sponge goes down by 5 millimeters. So this is it. There we are, right there. So 43 newtons. You need 43 newtons to push this thing down by 5 millimeters. Okay, I hope you found this video useful. More will be coming.